Welcome. Today I'm going to talk to you guys about accuracy and precision. Two words that I think most adults would agree seem like they're synonymous, but is not actually the case in science. You've probably used accuracy and precision in your chemistry classes when you've done some measurements and maybe had some experiments that you've worked on. The accuracy and precision do come up often in physics, so we want to make sure that you've got a pretty good sense of what that looks like. This is video 003 on accuracy and precision, and it has a few slides in it, but I'm going to try to whip through it since this should be a review for most of it. So we start off with accuracy, and accuracy is probably, I think, the easiest to remember. So if we take a look at it, I'm going to get a blue color here. Let's imagine for a moment that we have a value and we're going to do some experimentation. And that value, let's say, is 10. So this is the accepted value for x, which is 10.000. It doesn't really matter what it is. Now, if someone were to come along and do an experiment to be able to determine what that value is in our lab, you could compare this value to the value that they get and then see how close it is. And that closeness would be reported as your accuracy. So let's say we have two groups. So let's say team A finds that the value for this x in their experiments is 10.455. And then there's team B that finds that the value that they got is 10.036. So using those two values, you can make a judgment about which team had a more accurate result because you're going to compare both of these results back to that original accepted or expected value. So what we're saying is this is what we're shooting for. Can you get that? Can you confirm that that's the value for our lab? So I would say that this team did a pretty good job of confirming that 10.000 is the value for x. This team, on the other hand, maybe not so much. And so we could make a statement about the fact that they have increased error in their measurements. So their error is higher than this team. Now, you could then go back and analyze what kind of error they had based on their data set and so on, their methods, whatever they did. And that is the subject for a different video. So we're going to talk about that later on. This team, on the other hand, had a much smaller error. And we would say their value is much more accurate because it's closer to an expected value. Now, the expected value doesn't necessarily have to be exactly what the true value is. It just could be the value that we thought it might be, or the value that the claim implied it might be. So in the last video, we talked about claims and evidence. The evidence would be measurements. Maybe a claim would have an expected value for a certain measurement, and then you go do the measurements to see if you're close to that expected value. So how accurate you are is how close you are to that expected value. I think it's pretty straightforward, but it has to do with that error, which we'll talk about later on. Okay, compare that now to precision. And so precision is a little bit different. Precision has to do with how close a data set is. So let's say you were doing that same experiment. Remember that the accepted value for for x was 10.000. Now let's say that you're the team that had the closest value, which I think was 10.036 if I remember. So their average, and average for that team, average is usually with a bar above it, was 10.036. So let's say their data set looked like this. 10.036, 10.037, 10.040, 10.032, and 10.034. Okay, so that's their data set there. And they only did 5 trials, which is not a lot, but it is what we've got to work with. So I just made these numbers up. I don't know if their actual average is 10.036, but I tried to configure it so that it was pretty close. Um, so these are these values are pretty close. You would agree that the 10, the 0, and this first 0 after the decimal point in the tenths place, there's something that you're going to get every single time. Now, what happens in the next digit is a little bit up for grabs, but the first 3 digits there are digits that I would say you are pretty confident about. So you're confident about those 3 places right there. That's pretty good confidence in your measurements. So I would say that since you have, and then this value, of course, is pretty close. It's either 3 or 4 for each one. So if you've got that many digits that are pretty consistent, this one's not quite as consistent, but that many digits that are pretty consistent, you could say that you had high precision, which is exactly what we aim for every single time we do an experiment or a lab activity, is the highest precision, the highest repeatability of our measurements. Using this as an example, if you continued to have the same measurement techniques, you could predict that you would probably get values that had a 1 in this digit, a 0 in this digit, a 0 in this digit, and then either a 3 or a 4 in this digit. Now, what they get in the last one, you don't know. That could be all over the map. But again, 1, 0.03, or 4 is pretty good as far as what you're going to get over and over and over and over again if this is anything to judge by. So I would say that's pretty high precision. And that's what we're aiming for here. Now, I want you to take that into account here for the next slide. Take a look at what this means. So for us, that means that we have something called confidence, right? Now, you might say, I'm a pretty confident person. I have great math ability, so I'm confident in my abilities to be able to do experiments in physics. That's not what I'm talking about here. I'm talking about how confident are you that using those methods and those tools, someone will get the same measurements that you do. So going back to that data set again, we found that most people, or that most times that you did it, people had, or you had, I should say, the same values each time, roughly the same values each time. Something along those lines. And then you had some digit here. Doesn't really matter what those digits were. You don't know. That's okay. And it was followed by something else. So you've got those measurements. You will agree that those measurements are pretty close together. This is a 0 right there. Oof, ugly. So would you be confident that anyone using your methods and your measurement tools would get a 1 in that place, and a 0 in this place, and a 0 in that place, and then a 3 or a 4 in this place? I think you would be pretty confident about that. And so the more precise you are, the more confident you are in your measurements. So really, when I talk about confidence, that's what I'm talking about. And this is why we have to focus on precision, because we want you to be confident in your responses and your answers. And if you were to report out your results from an experiment, you want to also report out how confident you are that the results that you got are the actual results. So physics and most science has a very strict rule about what the confidence should be, but that's not something we're really going to talk about in here because it involves a certain amount of math that we're not going to do. And that's okay. You're welcome. So now, how do we report that precision? Well, here's where everything goes wrong because you guys may have had to experience this in your chemistry classes before. However, we do this now for the entire year, and that is we work on something called significant figures. If you have never heard of significant figures before, you are in for a treat. Significant figures are a bit of a pain, and they are important for every single answer that you give in this class. So you want to make sure that you are always taking into account the number of significant figures that you have in an answer. And really, the significant figures that you have in an answer is a measurement of your confidence. So let's go back to the precision discussion we had just a minute ago. If you know that you had a measurement that looks like this, and another measurement that looks like this, and another measurement that looks like this, and one more with a 3, and one more with a 4. My question for you would be, using those data, can you tell me how confident you are in your ability to measure repeatably the same number? I would think that you're talking about only a change of plus or minus 1/100th of the value there. Um, that's a pretty small amount. And so we would say that you have a pretty high precision. And that precision is, again, based on the number of digits that are repeated in your measurements. So you are repeating 4 digits in your measurements. We would say these values have 4 sig figs. The first 3 are all going to be the same no matter who measures it if they use the same methods and the same tools. The last one is estimated, and it's always, in any measurement, the last place is always an estimated digit. So the fourth significant figure is always somewhat estimated there. So you got 4 sig figs there. That's pretty decent. You probably were in a chemistry class where they always gave you 3 sig figs and said just worry about that. But for us, we have to determine the correct number of sig figs. And the correct number of sig figs is really based on your technique and your measurement tool. Notice here, I'm not able to get much better, much more repeatable than these 4 places. Remember, we had a digit for each one that was all over the map, but we just truncated that and rounded it off to the ones that were actually repeatable. And so we have 4 sig figs. So what we're saying when we say we have 4 sig figs is that no matter who does the measurements, people are going to get 10.03 or 10.04. And it's going to be that repeated no matter who does it. You can see immediately why if someone gives me an answer like this, I think the length of it is 10 centimeters. 10 centimeters. What you're telling me is it's roughly 10 centimeters there. It could be as small as 9 centimeters, or it could be as large as 11 centimeters. So this value has a very low precision. Being off by 1 centimeter either way is it's a lot of error right there. But look at this. If these are all length measurements, this is being off by a much smaller amount. So let's say these are all centimeters. So hundredths of a centimeter is what you're off here. That's a really small amount. That's tenths of a millimeter. So you're really doing a good job with your measurement techniques and your measurement tool if you have that many sig figs. Here we have very few sig figs. Here we have much more sig figs. If I put a decimal here, which we'll talk about in a minute, you'll see that there's 2 sig figs here, right? This one and that one. This is the one that everybody's going to get, and this is the one that's estimated. So it's going to be between 9 and 11 centimeters for an answer. So very few sig figs means lower confidence and less precision. No, larger number of sig figs means larger confidence and larger precision. So let's take a look at what that actually looks like here. All right, so I'm going to give you the rules for significant figures here very quickly. Then we're going to do a lot of practice with this, so if it's not something that you're familiar with, don't freak out. It'll be okay. We're going to take a look at what that looks like here. No problems. So on this side, over here, I'm going to go ahead and put the rules, and I'll pop those up as they come. And then on this side, I'm going to give you some examples. So here we go with the examples very quickly. For any digits in a measurement that are non-zero, like let's do 12.34. If you reported that out, wouldn't you agree that the person who reported it probably measured that that place was a 1, that place was a 2, that place was a 3, and that place was a 4? I think you probably would. Let's say it's meters, so 12.34 meters. In that case, any number, any digit that's not 0 is significant. So if you write it, that means you feel confident about it. And so you want to make sure that you only write down numbers that you're confident about. So in this case, we have 4 sig figs in that answer, because all of those were written down. The person must be confident in them, and so each, you can see there's 4 digits there, and so that's a pretty accurate or pretty precise measurement. Let's go on to the next one. What about zeros? Zeros are the trick, so you want to be careful about how zeros work. So let's do 10.04. So similar to the one measurement we just did, only you see that it has zeros in it. In this case, the zeros are between 2 non-zero numbers. So it's like a sandwich, right? So you get the bread is the non-zeros and the meat is the zeros. Well, I think you'd agree that if you wrote this down, you actually meant that you were confident in the 1 and the 0, and then in this 0 and that 4. If you weren't confident in this, you certainly couldn't write that down, right? If you didn't know that for sure that was a 0, how could you figure out what the 4 was? That doesn't make any sense. So you must be confident in all 4 of those digits, and therefore you have 4 significant figures. Hopefully everybody's with me so far. That was rule 2. Rule 3 is a little bit trickier, so just keep this in mind here. If you have a value with leading zeros, like this, there we go. So let's say the measurement is 0.0034 meters. Those leading zeros don't actually count as significant. Here's why. You know that the metric system is made up of units that can be scaled up and down, right? You can have meters for length, or you could have centimeters, or you could have millimeters, or you could have decimeters, or you could have kilometers. You could have all these different lengths of length measurements, sizes of length measurements. And they all have to have the exact same number of significant figures. So if I have this value right here, which is 0.0034 meters, and I write this as millimeters, it's going to be the same length, just written in a different unit. So this converted to millimeters is actually 3.4 millimeters. Does that make sense? I hope that makes sense. That's an M right there. So all you're doing, if you report out this value, is saying I have to use meters, but really the value is 3.4 millimeters. That's a better unit to use. But in physics, we often use meters instead. So how many digits are there that you're confident about in 3.4 millimeters? The answer is only 2. So would you agree that these zeros don't actually count as significant digits? It's only the 3 and the 4, because these zeros just hold the place. They are just placeholders. They do nothing else other than move the 3 and the 4 to the right, make them smaller values. So leading zeros don't count if they're after the decimal point. So that only has 2 sig figs. Now the last rule is the one that I think most people have the most confusion about, and that is the trailing zeros. So let's say we have 12,000 meters. I put a comma in there. I don't normally put commas in there, but I put a comma in there so you could kind of get a sense for what that looks like. Now the same rule applies from here down here. If I change the unit to something that's a little more appropriate for it, it has to have the same number of significant figures. So 12,000 meters is the same as 12 kilometers. There we go. There it is, 12 kilometers. So if I were to report out that length, I would be sure about the 1 and I'd be sure about the 2, and that's what I would report out, 12 kilometers. I think you'd agree that anyone who reported that out would say they only had 2 sig figs on that. So for this measurement, which is exactly the same, just with a different unit, it has to have only the same number of significant figures. So in this case, the number of sig figs again is just 2 because of the fact that every unit has to have the same number of significant figures in it. So if I change it, it must have the same number of sig figs. Now, there are some ways to fix this a little bit. So let's say you have 12,000 meters and you actually mean 12,000 meters. So there's my value. And I actually mean that I measured out this is 12,000 and 0, 0, 0 right there. I know for a fact that this is a 0. So one of the ways that I can report that out and change from 2 sig figs, see only these 2 are significant down here, one of the ways that I can change this into all of these being significant is I can put a decimal right there. If I put the decimal right there without anything after it, that means I know that I measured all of these things. And so as a result, this ends up with 5 sig figs. The other way to do that is to use what's called an overbar. And I use the overbar actually quite a bit, so you got to get used to it. So 12,000 meters, again, written that way is only 2 sig figs. But if I take this overbar and write it over the last significant place, it tells me how many significant figures I have. That overbar indicates the last place that I actually measured with a measurement device. And so in this case, it also has 5 sig figs on that one as well. So either one of those tools work. In fact, you can use the overbar for whatever you want. Let's say you're one of those people who doesn't like to round things off. Let's say your answer is actually 1.36, but you're only able to have 2 sig figs on it. For that answer, you go ahead and put an overbar above the 3, and you don't have to round anything off. You can just leave it at that, and you won't. You'll get proper credit for your response. So those are the rules for sig figs. Kind of tricky. You may have, like I said, you may have learned them before, but it's definitely something that we take into account more than was probably taken into account in your chemistry class. So please make sure you're ready for that. Okay, with that, I want to thank you guys for watching. Today I know it's not a fun one to try to get through, but it's one that, again, you are tested on again and again and again in this class. Every assignment you give me, every lab that you turn in, and every test that you take, if you don't have the right sig figs, you're going to get points off. So you want to make sure that you are always taking that into account. I always want to know that you think about error and confidence when you report something out. So please make sure that you do that. All right. Don't forget to fill in the note sheet and to go ahead and do the Google form with your question. You can ask lots of questions. We're going to spend the next day doing a lot of practice to make sure everybody remembers what to do with significant figures and how to work with them in class together. So hopefully that'll take away some of the fears that you might have. Again, if you have any questions, let me know. Thanks for watching.